Hi, I'm Jamie Batts, your instructor for A&P2. We're going to continue on with our review of kidney anatomy and physiology, and we just finished talking about the collecting system and the structure of the nephron. Now we're going to get into blood flow. This is really important to understand how the blood gets into and out of the kidneys, because remember, 25% of your cardiac output is going to your kidneys. So where does it go, right? We can assume the renal artery and renal vein, right? But how's it get into the glomerulus? That's what we're going to look at. So, whoops, screen share mode would help. There we go. Here we go. There we go. All right. So our renal artery ultimately is getting that blood to the kidney. It branches, though. As soon as it enters the hilum, it branches into segmental arteries. The segmental arteries then branch into interlobar arteries. Look at that word, interlobar, like in between the lobes. Remember the kidney lobules where you have a medulla, a renal pyramid, and the cortex? These are literally the arteries that are going in between those renal columns or within the renal columns going past the pyramids, right? They're going to branch into arcuate arteries, which arch over top of the renal pyramids. The arcuate arteries then will branch into cortical radiate arteries. These cortical radiate arteries are like little, think of that word radiate, like radiation, like the sun rays. Right? These are like little sun rays coming off of those arcuate arteries. They're radiating out all around the kidney and into the medulla to create these afferent arterioles. Afferent arterioles supply the blood to the glomerulus. Where does the glomerulus go? Well, the glomerulus is that big old capillary in the renal corpuscle, which is where all the magic happens, so to speak, in the nephron. This is where all the filtrate is beginning to form. So here is the whole breakdown of it, right? Renal artery to segmental to interlobar to arcuate to cortical radiate. From the cortical radiate, you can zoom over here to this other picture. Then you see these afferent arterioles, which are those little balls, right? Or the little line leading to the little ball, right? And the little ball is the glomerulus, right? Which is within the renal corpuscle, which is the beginning of our nephron. So then you say, okay, well, where does the blood go then? That's the next step. So from our afferent arteriole, that is supplying the blood to each nephron. Each nephron has an afferent arteriole. Then you have the glomerulus. Our glomerulus is where all that filtrate is formed. There is still stuff in the blood after filtration has happened in the glomerulus, right? There's lots of stuff that's stuck in the blood. Not all of the water leaves the blood. Not all of the solutes leave the blood. Some of it's left in. That stuff goes to the efferent arteriole. That efferent arteriole exits our glomerular capsule there, our glomerular corpuscle, and will go back into our renal vein, but not quite yet. There's also peritubular capillaries. These peritubular capillaries are that spiderweb network that overlaps the entire nephron structure. So anytime there's water or solutes being reabsorbed from our nephron loop, PCT or DCT or collecting system, it's going to be sucked up by these peritubular capillaries. They're collecting all of the water and solutes that were reabsorbed from our nephron. These are going to drain into the cortical radiate veins. So the efferent arteriole carries the leftover blood from the glomerulus to the peritubular capillaries. Peritubular capillaries pick up all of the extra reabsorbed stuff from the nephron, all leading back to the cortical radiate veins. Can you figure out how it gets back to the renal vein from here? Cortical radiate vein. And then we're going to go into our arcuate vein, into our interlobar vein, etc. So there you can see the cortical radiate vein. You can see that spiderweb network. It legit is just like that, right? Just a whole network of capillaries surrounding this whole structure. Anything that's reabsorbed is just going to be taken right back into our blood. So our juxtamedullary nephrons are a little bit different at this point. They do have peritubular capillaries. However, there's also something called a Vasa Recta. This Vasa Recta is literally like a parallel vessel to our nephron loop. So it's connected to our peritubular capillaries, but it's a long, straight, it literally parallels the nephron loop. And what this does is it's going to help pull extra water and solutes out of the filtrate. Remember, the function of our juxtamedullary nephrons is to hyperconcentrate our urine. And so that's what this Vasa Recta does. It hyperconcentrates our urine, and it drains into those cortical radiate veins. There you see literally like a parallel network coming off of the peritubular capillaries of the PCT and DCT. It goes down here, and then we'll go to the cortical radiate vein. So from the cortical radiate vein, it goes to the arcuate veins, then the interlobar vein, which then drains into the renal vein. The renal vein leads to the IVC, which of course goes back to the right atrium. So there's this whole flow of blood right back. It skips segmental veins. Notice there's no segmental vein. There's just interlobar to renal. So how are our kidneys innervated? Each kidney has over 1 million nephrons in it. Both the cortical and juxtamedullary nephrons are innervated by renal nerves. These renal nerves come in through the hilum. They follow the same branches of the renal artery. And most of the nerve fibers in the kidney are sympathetic, right? Hence, you get really nervous, and then what do you have to do? Oh my God, I gotta pee. Woo! Right? It's because of that overstimulation of your kidneys. It comes from the postganglionic fibers from the celiac plexus and splanchnic nerves. And that sympathetic stimuli is going to help adjust any of the blood flow and blood pressure within the glomeruli and stimulate the release of renin. What does renin do? Do you remember that? Renin stimulates the formation of red blood cells, right? EPO. Right? Renin's going to stimulate the release of EPO, which then stimulates red blood cell production. Sorry, thirsty. Talking about hyperconcentrating your urine here. It's a great time to answer these 3 questions while I take a sip. Let's keep going. All right, then we're going to go into the next section, which is our physiology here. I've alluded to some of it. We were just going over the anatomy piece. Let's talk about all of this physiology. It's physiology intense, which is one of the reasons I like it. I love physiology. The anatomy can be a little boring, right? This is this and that is that, but this is how it all works, which is really cool. So our urinary system is one of our main homeostatic centers of our entire body. It regulates blood volume and blood concentration. And if you don't have your blood volume and blood concentration regulated, you got nothing. You need to regulate that. So super concentrating our urine to help conserve all of the valuable nutrients and solutes and water that our body needs. All of the solutes, especially metabolic waste, are excreted in our urine. So urea is one of the products that is excreted in our urine. It's the most abundant metabolic waste product. This is a byproduct of the breakdown of amino acids. Creatinine. This is another byproduct of metabolism. It's a byproduct of creatine phosphate breakdown. Creatine phosphate is another form of energy, kind of like ATP, adenosine triphosphate. Creatine phosphate can act as a substitute there for ATP. It also helps get rid of uric acid. Uric acid is, a byproduct of recycling nitrogenous bases from RNA just in the process of protein synthesis. So lots of metabolic byproducts being eliminated through urination. This is a look at the normal values of solutes in our urine and blood plasma. So notice our urine is how we get rid of most of our extra potassium, as well as sodium. Our bicarbonate is mostly conserved, unless for some reason we're a little on the alkaline side, which isn't very common. We're usually a little more acidic. So our urine doesn't typically have a whole lot of bicarbonate in it. Same thing with glucose. Glucose is almost never eliminated in our urine. One, because it's a fairly large molecule, so getting through the glomerulus is pretty tricky. But it's also not eliminated because our body can store it, right? So unless you have really elevated blood glucose levels, maybe you're pre-diabetic or you have some type of insulin resistance going on, your body's typically not getting rid of glucose in the urine. Lipids, same way. Lipids are very large molecules. You're not getting rid of them. You're going to store them for later. Same thing with proteins. Proteins are even bigger molecules. And if you have protein in your urine, then you have something else going on in your body. You should not have protein in your urine. Proteins are humongous molecules. And the glomerulus is this really tight capillary network. So if you have these huge molecules kind of busting through, right? If this is your tight capillary network and your proteins are busting through, your capillaries are going to be damaged, right? You're going to get kidney damage, even kidney failure from all the proteins busting through. But you do get lots of nitrogenous waste from the metabolism of proteins in your urine. Oh, good question. I know someone was asking it. Do you have to know these numbers? What do you think? No, don't know the numbers. But I might give you a scenario where I say, you know, Jamie has a urine concentration of blah, 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 which is high, right? So I'd give you a scenario and tell you if it's high or low, and then you'd have to kind of dictate from that, you know, what's going on. So you don't have to know specific numbers like that. You can always look them up in a book, right, when you're on the job or wherever. You probably have to know for nursing school, though. I think you do have to know them for nursing school. So, all right, let's talk about how urine is formed. It's done through three processes make your urine: filtration, reabsorption, and secretion. Filtration, this is what's happening at the glomerulus. The blood pressure is forcing the water and solutes across that glomerular capsule or across the glomerular capillary into the capsular space, goes through the tubular fluid, right? Or goes through the renal tubule, which is the tubular fluid at this point. So the next step that happens is reabsorption. Your body says, whoa, we kicked way too much out. We need to reabsorb some sodium. Maybe we need some hydrogen ions and some potassium or whatever. So all that stuff's starting to go back into the peritubular capillaries, into the blood. Notice the word here on this slide. It says tubular fluid and peritubular fluid. Ooh, don't get mixed up in your terminology. The tubular fluid is the filtrate. Tubular fluid is the pre-urine. Peritubular fluid is the fluid, it's the interstitial space around our nephron and around our peritubular capillaries. So it's not in the blood. It's in the space that's not in the nephron and it's not in the blood yet. It's called the peritubular fluid or the peritubular space, right? Then we have secretions. Secretion is how we're transporting solutes from the peritubular fluid into our tubular fluid. So again, pulling stuff back in. This is done variably, but based on hormones in the DCT and collecting duct. There you see it, blood pressure pushing all of it out into the filtrate, reabsorption, pulling it back in from the filtrate tubular fluid into the peritubular fluid into the blood. And then secretion is the other way, going from the blood to the peritubular fluid to the tubular fluid. You can pause the video here, go back and review this little section on renal physiology overview. We're going to start talking about how our urine is formed. So each nephron segment has a particular role to play in the formation of urine. The filtration, reabsorption, and secretion have to be fine-tuned in each of these sections in order for urine to be formed properly. Filtration is only occurring at the renal corpuscle, and then the rest of the time it's this balance between reabsorption and secretion. So everything else can either reabsorb or secrete depending on. And when we say reabsorb, we mean take back from the tubular fluid back into the body, back into the peritubular space, into the blood, right? And so the regulation of the final concentration and volume of urine isn't done until the filtrate leaves the collecting system. So the collecting system and nephron loops all have to work together to get that final volume of blood. So here's another look now that we're ready to digest some physiology. Before we were just looking at the anatomy. It's the same picture we saw before, but let's look at it with a physiology viewpoint instead of just an anatomy viewpoint. In the glomerulus, you have all of your filtrate being formed through the process of filtration. We'll look at that in even more depth in a few slides, but that's the first step. So you have to have an accurate filtration that's going on. This is based on something called a glomerular filtration rate. We'll learn about it in a minute. In our nephron structure in the kidney tubule, right, the renal tubule, the first step in that PCT, the majority of the solutes are reabsorbed. The majority of the water is reabsorbed. Notice the direction of those arrows, and they're relatively big, meaning that there's a lot going on here. Variable solute secretion can occur here also, but it's typically, this is the site of most reabsorption. Nephron loop on the descending side, the thin segment, this is where we're reabsorbing water. On the thick segment, we're reabsorbing solutes. We'll talk about how that works in a little bit. Then in the DCT, it's mostly variable, solute and or water, reabsorption or secretion, whatever your body needs at that point. Same thing in the collecting duct, variable water and solute, reabsorption or secretion based on hormones and other inputs. So the renal corpuscle, the PCT, this is showing you the exact functions that go on there. I've summarized it already for you. Filtration at the corpuscle, PCT is doing reabsorption, again, 60 to 70% of the water and 99 to 100% of the organic substances. Like I said, the majority is done right there at the PCT. This is mostly done through active reabsorption, passive reabsorption, a little bit of secretion going on there too, putting stuff back in. But again, it depends on other factors for the secretion. Then in the nephron loop, we're mostly reabsorbing water, solutes on each side, right? The DCT is variable. The collecting system is variable, dependent on all of the input from our hormones. So, and then same thing with our vessels, right? The Vasa Recta, the peritubular capillaries, all redistributing the water and solutes that are going to be reabsorbed through the renal cortex or medulla, depending on which one. So I'm going to stop this video here so that you have a chance to soak up, reabsorb all of this information, and we'll start back in the next segment going into the nitty-gritty details of what exactly happens in that renal corpuscle. Ooh, a cliffhanger. See ya.